Good morning, guys. Hopefully I'll be here for part of today's lesson. I am going to go move rather quickly with today's lesson, and I will post this on Edmodo and YouTube, so if you want to go back and revisit it, you could do so. And I'll also post the notes, even though the notes are a little bit jumbled. All right, we're going to be revisiting logarithms and logarithmic functions, and I know students have often really struggled with this topic, so we'll kind of take it slow. I'll assume that you do remember some of this, but you need a good revision. So here we go. I want to remind you, and this is what we did yesterday, was dealing with exponential functions, right? And yes, or at least the day before, the exponential functions take this form of f of x equals a to the x power, which is 1-to-1, right? This is a 1-to-1 graph, therefore a inverse function exists, right? And if the inverse function exists, its inverse would look like this, right? We'd switch, this is our y equals a to the x, we'd switch our x's and our y's, and we'd have x equals a to the y power. Now, a has to be positive, and a can't be 1. Now, this right here, this inverse is so crazy important, it has a special name, and that is the log. This right here is the logarithmic function. All right, function. So when x equals a to the y power, that is the exact same thing as y equals log base a of x. So oftentimes, a lot of times I think students struggle with logs and how to deal with logarithms. I almost always in my head think about it in terms of the base to what power gives me x, or vice versa. Keep in mind that the domain of a logarithmic function is that x has to be all positive numbers. Because think about this, if I take a and I raise it to any power, negative power, 0, positive powers, this value right here will always be positive. Therefore, we can only plug positive values in for x. Therefore, our domain is all positive numbers. I have written in my notes from last year that a log is really just a name for a certain exponent, and I think we should just kind of write that down. A log is really just a name for a certain exponent. Okay. One of the things you're going to be asked to do on your homework is to be able to change back and forth between exponential expressions and logarithmic functions. So I'm going to raise this up. So this is how changing between exponential expressions and logs, and going back and forth. So here's a couple examples. So if you have 16 equals 4 squared, right? 4 squared equals 16. Another way you can write that in log, this is in exponential form, 4 to the second power equals 16. The way you write that in logs is log base 4 of 16 equals 2. 4 to the second power, what a log really equals, a log is an exponent. 4 to the second power is 16. Another example would be if I have x to the pi power, that equals e. So log base x of e equals pi. When I raise x to the pi power, I get e, or x to the pi power equals e. So one of the things then you're going to ask to do is to evaluate some logs. So just to review evaluating logs. So log base 3 of 1/9. And they're asking you, what does that equal? Well, this is saying 3 to what power? Oh, actually, I guess they're not asking you to even evaluate this yet. I'm asking you to write this into exponential expression. So this is in logarithmic expression, or logarithmic form. To write it into exponential function, it would be 3 to the negative second power equals 1/9. Another example of working backwards would be log base pi of x equals 1/2, and we'd write that as pi to the 1/2 power equals x. All right. Then they ask you, or at least I'll be asking, or you're expected to on your homework, is to deal with exact values. So to evaluate logs. So exact values. So an example of that would be if they gave you log base root 3 of 9. And they're asking you how to do that. So the way you could think about this is to deal with the fact that this is the square root of 3 to what power gives me 9. And using the methods that we used yesterday in our homework, you can say that this is 3 to the 1/2 power to x, and then 9 is really 3 squared. Exponents in this case multiply. So we have 3 to the 1/2 power equals 3 squared. And since our bases are now the same, we say for what x value 1/2 x equals 2. And so in this case, x equals 4. So this whole thing would equal 4. All right. Okay, keep in mind also regarding domain and range of logs. So one of the things you're asked to do is to deal with the domain and range of logs. So let's just quickly look at an exponential graph, right? So here's an exponential growth graph. Let's look at the domain. The domain of exponential growth I can plug is all real numbers, right? I can plug anything in for x. My range are all numbers greater than 0, correct? This will never cross the line y equals 0, and it goes on forever increasing. So keep in mind that exponential functions and logarithmic functions are inverses, right? These are inverses. Therefore, for logs, the domain is the range. So the domain is that x has to be greater than 0. There's not going to be any number that I can plug in greater than 0. And then the range is going to be all real numbers. So one of the things you're going to be asked to do, and I'll turn the page for you, one of the things you're going to be asked to do is to find the domain of a log. So here's the example. The example says, find the domain of the function g of x equals the natural log, and we'll revisit what the natural log is shortly, 1 over x minus 5. Okay? Now keep in mind, once again, that for any log, right, this is, by the way, natural log, in case you forgot, is just the log base e. And we could talk about natural log more in detail when I come back if you are very uncomfortable with e. We can talk more about that. So this is saying e to what power gives me 1 over x minus 5. Now keep in mind, when I raise e to any power, this will always be positive. This will always, always, always come out as positive. So you say, for what values would this be positive, right? We have to know for what intervals. This is what we did in chapter 3, for what intervals. So we know that x cannot be 5, right? Because that would be undefined. So we have the intervals from negative infinity to 5, and from 5 to positive infinity to know what's happening in this graph. So if you were to plug in a number smaller than 5, such as 4, right? 4 minus 5 is a negative 1, therefore this value would be negative. Anything greater than 5 would come out positive. Therefore, for my domain, this is my domain, all numbers greater than 5. So my domain would be either from 5 to infinity, or I could write it as just, x is greater than 5. And we could do our notation as such. Okay? All right, so that's one thing that you're going to be asked to do as well. In addition, you're going to be asked to graph logs. So to recap how to graph logs. So to graph logs, here's the trick. To graph logs, graph the exponential function. So graph its inverse. Graph its inverse, which you know how to graph exponential functions, and reflect over the line y equals x, right? We know that all inverses, their graphs are symmetric across the line y equals x. So reflect it over the line y equals x. So an example would be if you were asked to graph log base 3 of x, go ahead and graph 3 to the x power equals y. Graph its inverse. Right, so if we go to graph its inverse, So let's say negative 2. Let's do this. All right, at negative 2, we have 1/9, 1/3, 1, 1, 3, 2, 9. Let's see, 2, 4, 6, 8, 9. So it would be up here somewhere, right? This is the exponential function of 3 to the x power. The line y equals x looks like this. And if we were to reflect it over that line, instead of 0, 1, it would be at 1, 0. Instead of 1, 3, it would now be 3, 1. And then our graph, if it was, let's say, this point right here of negative 1, 1/3, it would be 1/3, negative 1. And our graph would do this. It would hug the y-axis and kind of continue on as such. So this right here is y equals log base 3 of x. All right. How to use transformations with, you can use transformations with logs. So here's a little tidbit on transformations. There's a lot in this chapter, in this section. F of x equals log of x plus 5. Keep in mind your domain. Your domain is that all of this x plus 5 has to be greater than 0. Therefore, x has to be greater than negative 5. So when you go to graph that, for example, and let me make sure you can actually see what I'm doing. All right, let me move that up. First step would be to just graph log base. By the way, if there's no base here, that's a base 10. Just to remind you, that's a base 10. Log base 10 of x, which would look like, let's see, let's get 1, 2. Let's do 2, 4, 6, 8, 10. It's going to be going through 10, 1 and 1, 0. And it's going to be kind of hugging like this. So graph log base 10, and then you're going to do a shift. Shift left 5. All right, so let's see, negative 2, negative 4. So and if this is negative 6, it would be shifting this way. So it would be at negative 4. We'd have an asymptote, kind of, not an asymptote, but ultimately x has to be greater than negative 5. So at negative 5, our graph is going to be, that's where our graph is going to be hugging. And then it would kind of come through here like that. This point would be shifted 5 units to the left. All right, last but not least, and I know I'm doing this very, very quickly, last but not least is how to, is about solving log equations. And I think I've given you a few of those as well. So here's an example. You're given log base 5 of x equals 3. Write this in exponential form. This is saying 5 to the 3rd power equals x. So what is 5 to the 3rd power? 125. Done. Next one I'll show you, and this is the last example I have for you. Log base 6 of 36 equals 5x plus 3. So this is really saying 6 to the 5x plus 3 power equals 36. Find a common base. So this is 6 to the 5x plus 3 power, and that's 6 squared. 36 is 6 squared. Therefore, 5x plus 3 has to equal 2. So 5x has to equal negative 1. So x is negative 1/5. Looks like a funky one. Negative 1/5. All right, if you have questions, post it on Edmodo, and I will see you guys on Friday. Have a wonderful day.